All right, let's get started. So, just a quick reminder before we get into some content. The project contribution is due Friday. If you're submitting a project contribution, make sure you get your pull request and get that in by Friday. I have a total of 3 submissions now, and I took a look at the submissions. 2 of those are from the same person for the same PR. So I have 2 submissions total. If that's not part of y'all's plan, you're just not doing the project contribution because you're picking 6 other application objectives. It's fine, whatever. I just don't want a flood of emails on Saturday saying, "Oh shoot, I didn't realize the deadline passed." So I just want to make sure I get that reminder out there. I probably won't remind you again on Friday. So reminder: project contribution deadline is about to pass in a couple of days. So if you plan on doing that, get it done. And I've had a total of 0 questions about project contribution. So I assume everybody's comfortable with that, knows what they're doing, has either chosen not to do it or knows what they're doing with it. I think I had 1 question in office hours, actually. Any questions about that? Ren has 0 AOs. Yeah, I get that. TA shouldn't have any AOs. Okay. Let's do some content. Let's talk about binary search trees. So today's lecture task 4 we are on, is to write this method named makeDecision, which takes a binary tree node of type decision tree value, which take a second to look through what a decision tree value is. That's an abstract class which has 2 classes that extend it. Decision node and action node, I believe I called them, which implement these 2 methods a little differently. Either the action node, or the action method, and the check method, which I should have put in quotes so they stand out a little more, but they have 2 methods. So for each decision tree value in this tree, you're gonna call check. Check is going to return an int. It's either going to be a negative int if you should travel to the left child of that node, a positive int if you should travel to the right child of that node, and 0 if this is an action node that should perform an action. If it returns 0, you're going to return the action returned by the action method of that class. So return that action up the tree, and then return that up the recursion until the root finally returns the action to be taken. So in this way, we're going to have decision trees, which are determining how an AI is going to behave, or rather what action they're going to take on that particular frame. But if you really look through the code, it's not quite frames. AI update their decision that they're making every 10th of a second, and the frames are working every, I believe it's 30 FPS, the way it's set up in the way I set up the repo for release. And that's what we want to do for this. I would say, for those of you asking about difficulty and everything, I would say LT4 is the easiest lecture task. This is, especially because I nixed the testing, this is the easiest lecture task. It's easier than even 1 through 3. This is the easiest one, because I nerfed it so much. But yeah, it's snowing here. It's not snowing right now, but we have about 3 inches of snow on the ground here in Buffalo. Those of you in Buffalo who are new here, welcome. This is kind of a regular-ish thing. Usually not this late in the year, late April, but Christ, it's a thing. It gives us nice variety in the weather, at least. We had a few nice days, and then it's back to winter. So let's talk about BSTs, binary search trees. This is a binary tree, just like we talked about on Monday, except it has these extra properties to it. It has these properties where for every single node in the BST, every node in the left subtree of that node has a value less than, or rather comes before, according to a certain comparator, In my language here, I'm assuming that the comparator is the less than operator and that the values are ints. So everything in the left subtree is less than that node, and that's true for every single node. For this node, everything in the left subtree is less than. Everything is in the right subtree is greater than. Everything in the right subtree is greater than 5 here. Everything in the right subtree is greater than 8. Everything in the left subtree is less than 8. This is true for every single node in a BST. And depending on the implementation, duplicate values are sometimes handled differently. Sometimes a tree doesn't allow duplicates at all. For example, if we're building a key value store, like a map, out of a tree, which often happens, which is often the underlying implementation, we just won't allow duplicates at all. Or we break ties arbitrarily. In my code later on, we're going to break ties by going to the left. If we had another 7 here, 7 would be to the left. And we'd say everything to the left subtree is less than or equal. But depends on what implementation you have, how you handle duplicates in a tree. But the first two, aside from the ties, this kind of edge case of ties, all the values in the left subtree are less than, all the values in the right subtree are greater than. And that's it. It's a binary search tree. That's what it is. So let's see this in the code. We want to implement this class, this binary search tree class, which is going to have a reference to the root of the binary search tree, which is going to be a binary tree node, just like we saw on Monday. It's going to have a reference to the root of the tree, where that would be a reference to this node containing the value 5 in this example. So we're going to have a reference to the root node. We're going to have a comparator, so we can compare things based on whatever comparator we want, just like we used for sorting. Same protocol here. Same comparators we use for sorting. And a type parameter A. So again, the tree example from the previous slide, A was int, comparator was the less than operator, and then we have a root containing 5. And then what we want to talk about for most of the lecture is these two methods, insert and find. Given this structure, how are we going to insert elements into a tree? And how are we going to find a specific element in the tree? So if we want to find a value A of type A and return a node containing that value, how are we going to do that? And that's what we want to talk about. So we already know the structure of a binary search tree. Everything on the left is less than, everything on the right is greater than, and ties broken differently based on implementation. And now we want to implement these two methods. And for example, if I wanted to create that tree from the previous slide, from the first few slides, give it the less than operator, make a tree of ints, insert 5, 2, 8, 4, 7, 14, negative 3. That should create the tree from that slide. And then if we do bst.find 4, we should get the node that was created when this 4 was inserted. We should get a reference to that node that contains the value 4. Yeah, exactly. I'm looking for questions in chat, and all I get is, why is A not green? Why do you want A to be green? You want the same syntax highlighting as IntelliJ? Is that what you're asking for? Yes, you'll be okay. I'm confident. You know, I actually said the same thing earlier in the semester. The syntax highlighting was different. Somebody was panicking. I'm confident that you're able to figure that out. I'll say that much. I'm confident you can figure it out. That this is the type parameter. If you can't, I don't know. You might not belong here. If you need the syntax highlighting that much, I like having a little bit of it just to show that it's code. But you shouldn't need the syntax highlighting. It's helpful. You shouldn't need it. I hope it was a troll. I'm assuming you were just trolling. I gave you a serious answer to a troll, but anyway. So let's do BST find. We want to find a node in this particular tree. And here's the code. This is how we're going to do that. In pseudocode, we're going to check if the value that we're looking at right now at the node we're currently considering, and we're going to start with the root. If the node we're currently considering, that value is less, if that value is greater than, if the value we're looking for is greater, if the comparator taking that value we're looking for and the value at this node returns false, or for our ints, the value we're looking for is less than the value at that node, we're going to move to the left child. If it's greater than, we're going to move to the right child. If it's equal to, we're going to return that node. We found what we're looking for. And if the node we're considering is null, that means that value is not in this tree. Blink twice for help. So those are 4 conditions that we're going to check. So when we call find, we want to find this specific element. I'm going to write this recursively, and I don't have enough parameters here. This isn't the signature that I want on my method. So I'm going to write a helper method and just defer to the helper method, because I want the helper method to know which node it's currently considering. So I'm going to start at the root, looking for A, and then call my helper method. The helper method is going to take that node, check if it's null. If it's null, return null, and that's our way of indicating that that value A is not in this tree. Else we're going to check our comparator. If our comparator giving the value we're looking for first, so we're saying if the value we're looking for comes strictly before the value we're looking at, if this comparator is less than, this would be A less than node.value. Then we're going to move on to the left. We're going to move to the left child of this node and make the recursive call and continue our search down there. If the value we're looking at comes strictly before the value we're looking for, that means that this value is strictly greater than the value at this node. And we're going to head over to the right subtree, check out the right subchild, and continue our recursive search over there. Else, so if A doesn't come before this node's value, and this node's value doesn't come before A, then we know that these values are equivalent according to this comparator, and we can return this node. We have an equality, return this node. You good, my guy? Yeah, my brain just didn't want to work for a second. Well, getting the wording on this is, when I'm trying to word it in terms of a comparator, it just takes some extra brain power to come up with that wording. If I just stick with less than, then it's a lot easier. But we want to make sure all of our code works with general comparators instead of just less than. Everyone good on this? So in your LT4, when you're thinking about a decision tree, navigating a decision tree and figuring out what decision to make, where you're going to have a tree, actually let me visualize this, where you're going to have a tree where each node is either a decision node, where it has a left and right child and you're deciding which direction to navigate. Either you have a decision node and you're navigating to another node, or you have an action node, which will be the leaves. And the way we'll build these decision trees is either a node has 2 children and is a decision node, or it has no children and it's an action node. So these nodes might be like move towards a player, stop, fire at a player, run away from a player. And then these nodes would be the decision nodes that decide, based on the current state of the game, which one of these 4 decisions am I going to make. That's what your LT4 is doing. So it might look very much like find. You're trying to find the leaf node that contains the actual action that you're going to be taking. Where does that comparator come from? It's part of the BST constructor. So BST takes a comparator. So these methods are inside. So I'm stripping out the rest of this and just taking the find method and implementing find right here. And then I write another method to help it out. But I'm inside the binary search tree class, which has a comparator as a constructor parameter. I followed your question up to the emoji. Why are you saying that's a joke question? A node doesn't know it's the previous node. It's like when we're when this is called, when we're at a node, we don't know where we came from. We just know this node. We only know about this node that we're currently working with. We don't know what the previous node was. We don't know if this is the root or not. We don't know if it's a leaf. Well, we could check if it's a leaf if we wanted to. Can we just check if A equals node? No, because node is a binary tree node. Which was defined last lecture. A node is a binary tree node which has a value, a left, and a right. A is of type A, which is not a binary tree node. But that's effectively what we do. Oh, no, we can't do that. No, I see your question. Can we just check if A, like, could we say A equal node dot value? No, we can't, because we have no guarantee that an equal method is defined. All we have is the comparator. We can only use the comparator. So if we say comparator of A node dot value is false and comparator of node dot value A is false, then they are effectively equal according to this comparator. And if that doesn't make sense, you got to go back to the sorting lectures we talked about. We talked about that at length. So you can't use equal because you have no guarantee that a dot equals method exists. Or if a dot equals method exists, how do you know that it matches the comparator? So maybe our comparator is comparing based on absolute values, and we have 2 and -2, and we're using equal. We're saying, well, these aren't equal. Well, no, but according to the comparator, they are. So you have to use the comparator to get that information. What is a node dot value ? A node dot value or a, I don't even know where you got that from. What are you even talking about? What is a ? A angle brackets node dot value or a node dot value. I am not able to parse this question. If you can reword that, I'd be happy to answer it. Oh, what's the comparator? Less than or greater than? Oh, I see. I'm reading the angle brackets as like a quantity, not as a less than and then a greater than. It's whatever, it's anything you want it to be. So whenever we create this binary search tree, in this example, in this slide, it's a less than operator, but it can be anything. It's whatever comparator we give the binary search tree when we create it. So in this example, from the previous slide anyway, it could be different each call of find because we could have different binary search trees with different comparators. But in the example from the previous slide, the comparator would be less than. Else if a less than node dot value, else if node dot value less than a. But we could just as easily on this slide flip this to a greater than, and then the comparator would be a greater than node dot value. We could change this to absolute value of a greater than absolute value of b, and that would be valid as well. Then this comparator would be a absolute value of a greater than absolute value of node dot value. It's whatever the comparator is, which the comparator can change. We can have a binary search tree with different comparators. And if I give you a comparator of greater than on a quiz, like 80% of you will get it wrong because you're hard-coded to use less than. I've done that in the past. Hell, I might do it next week. Any more questions on this? This is the most important slide. This is why I'm spending so much time right here. Clip me saying that it's important. I don't know if that'll be helpful. And you can't clip like the past 10 minutes of lecture. Instead of clipping things, if everybody just watched lecture in its entirety, you would do really well in this class. That doesn't apply to anybody who's hearing me say that, though, unfortunately. The people who need to hear that won't hear it until it's too late. Oh, yeah, clip. Oh, right. I was referring to the wrong thing. Yeah, clip me saying 80% of you fail the next quiz if I put greater than. I'll probably put something a little more obvious, like absolute value, just because it's harder to miss. Or I'll just chicken out and just go with less than. All right, let's move on then. So bst.find, if we want to find the value 4 in this binary search tree, we're going to start at the root. We're going to use our comparator. We're going to assume our comparator is less than. And put the fear in our hearts. Just pay attention to what the comparators are. It shouldn't be that hard, but it's something that so many students... I think it's just because it's the stress of the quiz that you're not looking and noticing that it's a greater than sign instead of a less than. That's why I'll put something more obvious than that. What's a comparator? So we're going to check if we're finding the value 4. Is 4 less than 5? Yes. So we're going to move to the right. Is 4 greater than 2? Yes. Or is 4, we would check, is 4 less than 2? No. Is 2 less than 4? Yes. So we're going to go to the right. 4 equals 4. So 4 less than 4, false. 4 less than 4, false. Therefore, we hit the else. And then we return this node. This node is returned up the recursion. And we return a reference to this node when we try to find the value 4. For the comparison function, I mean, if it's a less than function, then yeah, it doesn't imply it's explicitly computing that. When the comparator is the less than function, then that's exactly what you're doing, is saying no.value less than a. So that's find. Let's go on to insert. And we want to insert at a particular value. This is similar to find, but with just an extra step and a little bit more code to handle certain cases. So when we insert, we want to run effectively our find algorithm to find where this value it should be. And then once we reach a null value, we're going to insert the value there. And then if there's a duplicate, if that value is already in the tree, we have to handle that some way. I'm adding duplicates to the left, and I am allowing duplicates in this tree, according to this code. So when we insert, first we're going to check if the root's null. If the root's null, there's nothing in this tree. This is the first node to be added. So the root is going to equal a new node with this value, with no children. We have a tree with just one node. If the tree is not empty, we're going to call our insert helper, because we want an extra parameter as the node that we're considering. And start at the root and find where we're going to insert this this value a. And we're going to run our same checks. We're going to run our comparator. If the value is less than a, or comes before according to this comparator, which we'll assume is less than just because it's easier to say. If the value is less than a, then we're going to look to the right tree, where we need to move right, because A has to go to the right of this node. It has to be in the right subtree because it's greater than, because it doesn't come before this. So if the right child is already null, congratulations, we just found where to insert this. We're going to say node.right is now equal to a new node with the value A and no children. If the right node is not null, we recurse, we move to the right child, and we just keep moving, keep searching down this tree. If this node's value doesn't come before A, then A comes before or is equal to the node.value. So we're going to look to the left subtree. We're breaking ties to the left. If the left child is null, congratulations, we found where to insert this thing. Insert it. If not, we're going to recurse and move to the left. So if we have this tree where I removed 7, if before we have 7 added to this, and we want to add 7, we're going to check 7 compared to 5. 5 is less than 7, so we're going to move to the right. We're going to check 8 less than 7, which is false, so we're going to move to the right or to the left. That node was null. So we're going to create a new null node and have that be the left child of this node 8. Your right child is null. Could be bullying if taken out of context. There are actually people with the name null. I think there's a family with the last name null. Causes a lot of issues in databases in a lot of our code. Shouldn't, not these days. It shouldn't cause any issues. But there have been in the past sloppy developers having a string with the literal value null as their null value. Causes issues. What if 8 had a child and it was 6? So if 8 had a child and it was 6, then we would go move, recurse, move, look at that node, and then look to the right, and then add 7 to the right as a right child of that 6. Oh, I get that question. Why was 4 on the right of 2 and not 3? 3 is the negative value. If 3 was positive, 3 would be right here, and then 4 would be over here, depending on the order in which they were inserted. Everyone feeling good about insert? How do you sort a binary tree? Oh my goodness, I'm so glad you asked. A binary search tree, at least. How do you sort a binary search tree? Is the question I want. How do you sort a binary search tree? It's already sorted. You run an in-order traversal on a binary search tree, and you'll get all the values in order, in sorted order, according to the comparator that you were given. How do you reverse a binary tree? Do you actually want to reverse a binary tree? Or are you just asking silly questions? So when we run an in-order traversal, we make a recursive call on the left child, handle everything at the left, then visit the node that were the node itself, and then we make a recursive call on the right. So with our binary search tree, since everything on the left is less than, everything on the right is greater than, and we're visiting this node right in the middle of all of the values less than and all of the values greater than, we must be visiting them in sorted order. So we're going to the left, null, null, well, null, visit, null, -3, visit 2, go to the right, visit 4, return, visit 5, right subtree, left subtree, visit 7, return, visit 8, right subtree, visit 14, return. As long as the property of a binary search tree is valid, every node has everything on the left subtree less than, everything on the right subtree greater than, an in-order traversal is going to visit all the nodes in sorted order. If you want to, you don't really reverse a binary search tree, but if you gave it the reverse comparator and then visited, actually, no, I have a better answer for this. Instead of in-order traversal, you would do, I guess, what would be called a reverse order traversal, where you would visit the right node. You wouldn't actually reverse the tree, first of all, but you would make your right recursive call, then visit the node, and then make your left recursive call. And it would visit these in exactly the reverse order. I'm interested, but Jesse shuts me down. The 3 question marks made me suspicious, is what it was, by the way. 3 question marks sounds sarcastic to me. Would it be possible to link multiple binary search trees, or would that crash the code? Again, it depends what is that something you're actually trying to do? As long as the property holds, like if you have a binary search tree where every value is less than -3, and you want to add that as a left subchild, and have this refer to the root of that tree as its left subchild, then sure, that's fine. but you have to maintain the property of a binary search tree. Everything to the right's greater than, everything to the left's less than. As long as that property holds, you can combine these in any way. That's not going to hold in general. When you have two binary search trees, they might be, it might not be an easy way to combine them, except navigating one of the trees and manually adding every element into the other one using its insert method. Wouldn't that return 7 before 14 in the reverse order? No. So we go to the right, go to the right, go to the right. That's null. Visit 14. Return, visit 8. Left subtree, null. Visit 7, null. Return, return, 5. Left, right, 4. 2, -3. They would all be exactly the order you want. That would be exactly the reverse order. To get 7 first, you would go to the right and then completely forget that we're doing a reverse order traversal, and then for some reason go to the left first on 8, just like it were a regular in order traversal. And that's mixing two different algorithms. You want to see the code for the traversal like we did last time? I don't think I have the code in these slides because we talked about it at length on Monday. Just go to Mondays. Go to the in-order traversal and swap the right call and the left call. That's the traversal. We tried inserting 5. Ooh, good question. Yeah, it would end up being to the right of 4 in my implementation, which I'm not super happy with, but yeah, it would be to the right of 4. And that's why a lot of times trees just won't allow duplicates at all. They're going to see that the value equals 5 right at the root, and then say, we're not adding this to the tree, and just reject the duplicate. In my code, right, it would be to the right of 4. Yeah, I'm not going to ask about stack and heap too much. Heap for linked lists and binary trees is going to be disgusting. The only reason I'm not asking about stack and heap on these questions is because you should know it inside and out by now. The fact that you're commenting that it would be disgusting to go through the stack and heap on trees and linked lists makes me want to add those questions to the quiz. You should be at the point right now where you're like, well, if he asked about stack and heap on these things, that's no big deal because I know stack and heap like crazy now because he's been talking about it all semester. Like if I'm wrong about that and that's not the case, priest, then maybe those questions will show up on the quiz next week. Yeah, and everybody can blame priest for that. If I ask about stack or heap next week, I want everybody coming back and blaming priest. All right, so let's talk about let's talk about efficiency a little bit. So a little bit of vocab. A balanced tree is a tree where each node has the same number of descendants on the left and right subtrees. This is a perfectly balanced tree, and it looks nice visually on the slides. That's why all my trees are balanced. That's one reason why all my trees are balanced. So, and if a binary search tree is balanced, we get some really nice properties. The height of the tree, meaning what's the maximum number of children that have to be visited in order to reach a leaf in the tree, is O of log n. Insert and find, both those algorithms take O of log n, because each one of them, each time they did a constant amount of work, they visited a child node. They moved to one of the child nodes and started moving down the tree. So any path from the root to a leaf is going to be O of log n. So insert and find are going to take O of log n. Very efficient algorithms. O of log n is, extremely fast, even for very large trees. Quick question. If a tree has 1 million nodes in it, 1 million nodes in it, and it's perfectly balanced, what's the height of that tree? How many children do you have to visit to go from the root all the way to finding a leaf in that tree. If we go, like for example, this is a tree of height 3, and we have to travel 2 times to find a leaf from the root. And we have 7 nodes in this tree. 7 nodes, and we have to travel twice to get from a root to a leaf. If we have 1,000,000 nodes in a tree and it's perfectly balanced like this, so each one of these will have 2 children, each one of their children has 2 children, etc., until we have 1,000,000 nodes in that tree. What's the height of that tree, and what's log n of that? What's log of 1,000,000? Log base 2 of 1,000,000. I'll give you a hint. Bex is way high, way above the estimate. 1,000, that would be the square root of 1,000,000. Log is way less than a square root. 1. It's not 1. It's 20. It's like 20-ish. Yeah, exactly. 20. That's how powerful log is. When you see a log n runtime, even when n is 1,000,000, log n is 20. Very, very efficient. Extremely efficient. We also happen to get an n log n sort time. If we want to sort using a tree, we're going to insert all the values into a tree and then run an in-order traversal. And we can do that in n log n time. So n times log n for each insert, and then constant time, or n log n, I always forget, to actually do the traversal itself. So we effectively have a new sorting algorithm. Well, kind of. There's a caveat that we'll talk about in the next slide. But we effectively have a new sorting algorithm where the sorted order is maintained even as elements are being added into this data structure. And in fact, we can actually remove nodes in log n time as well. So if all our operations are log n, every time we modify the tree, it only takes log n, and we maintain the sorted order. Right, 19.9315. If it's 1024, you'll get 20 exactly. 1024 is the magic number there. Or oh no, I said 1,000,000, didn't I? 1024 squared, whatever that is. So we get log n inserts, log n deletions. So if we have data that's constantly changing, and also we want to maintain that data in sorted order. So maybe we have something like a leaderboard where a bunch of players, their scores are changing constantly, and we want to maintain a leaderboard, maybe a global leaderboard of a popular game where we have millions of users, and we want to constantly maintain that data in sorted order. There's a few ways we can do this that are bad. First, we can do an array where every time we change a value's position, it's going to take O of n time because it takes O of n time to insert into an array. We could use a linked list, which is going to take O of n time just to find where to insert a value or where to move a value to and from. And with either of these data structures, we might be like we can just prepend to a linked list and then call sort and have n log n runtime every single time. That's inefficient, horribly inefficient too. With a tree, we just have log n insert it, and it's still in sorted order. So very efficient to maintain data in sorted order when you expect the data to be constantly changing. So that's one big advantage of using trees. There's one huge problem with this. Is I was very careful in the previous slides to insert in a certain order that's going to maintain balance in our tree. But what if I didn't? With the code that I showed you, if we insert the values in sorted order, we're going to get something like this. Now our find and insert is going to take O of n time, because if we want to insert 15 to this thing, we have to navigate every single value in this list and then add it here. That's not good. We're effectively a linked list at this point. We get O of n operations of any of the basic operations we want to do, and we've completely defeated the purpose of talking about trees, and we might as well just use the linked list in this instance. So we have to be very careful about how we insert things. So how do we insert things in log n time while keeping the tree balanced? How would we remove a node and keep it balanced and maintain the sorted order? How do we handle duplicates? Well, duplicates we can just ignore completely. If we don't allow duplicates, that's fine. But how do we maintain the balance of a tree and still insert, find, delete in log n time? All excellent questions that'll be answered in CSE 250. So that's my little advertisement for CSE 250. You're going to answer those questions and figure out how to create what's called self-balancing binary search trees that maintain the balanced order even if all the values are inserted in sorted order. What it'll do is change the structure of the tree as it starts getting lopsided. So once this 4 is added, this tree will actually shift, turn 2 into the root, -3 will be the left child of 2, and 4 will be the right child. And as it gets more lopsided again, it'll keep fixing itself as nodes are inserted into it. And that's something you'll learn all about until you're sick of hearing about it in CSE 250. That brings us back to our lecture tasks. Given a binary search tree, given a binary tree of decision tree values, navigate the tree given the structure of a decision tree value to be able to find which leaf or which action should be taken.